Why is the Sun said to be a third-generation star? And what about the remnants of its previous generation? Were the neutron stars or black holes? Where are they now? The story begins 13.7 billion years ago. At that time, the universe consisted almost entirely of hydrogen and a small amount of helium. Slowly, they formed vast molecular clouds. Under some perturbation, these molecular clouds began to gather into clumps. Subsequently, these clumps of matter, like a snowball effect, gathered more and more, growing larger and larger. When they reached a certain size, as hydrogen in the core began to fuse, the first stars in the universe were born. They are also called population 3 stars. Although, as of now, we have not truly observed a population 3 star, we can still make some speculations about what they were like. For these first stars lacking heavy elements, they might have been rather puffy, many being massive giants over 100 times the mass of the Sun, due to poor nourishment and a simpler composition of elements. The fusion reactions inside these stars were also quite primitive, making it difficult to generate enough energy to support their enormous bodies. Therefore, the lifespans of these giants were very short, perhaps ending their lives hastily in just a few 100,000 years. However, after this rough processing by the first stars, the universe now contained small amounts of metallic elements. Many of these metallic elements gathered near the galactic bulge at the centers of galaxies. And so here, the second generation of stars, containing small amounts of metallic elements, were born. Quickly, in a universe less than 100 million years old, the second generation stars became dominant. Note that each generation of stars here is only roughly divided based on their metallicity, metal content. It's not strictly the first batch, second batch, because the collapse of molecular clouds is random. Stars of each generation were not born simultaneously, nor did they die simultaneously. The generations of stars are more like seniority in a family. Moreover, the birth of stars is different from having children. They might not have so-called direct relatives. The raw materials forming a star might come not only from a specific previous generation star, but also from material ejected by other stars, or even include primordial interstellar material from the Big Bang. Similarly, for so-called third-generation stars like our present Sun, also known as population 1 stars, the material that constitutes them also comes from these sources. It's just that compared to the second generation, the metallicity of third-generation stars is yet another level higher. Actually, from a temporal perspective, we can also see that the Sun should belong to the third generation, because the lifespan of the first generation stars is measured in millions of years, which is almost an instant for the 13.8 billion-year-old universe. So, the emergence time of the second generation stars, on a cosmic scale, is almost simultaneous with the grandparent generation of the first stars. Therefore, if a second generation star could live until today, it would at least be an old-timer of 10 billion years. But our Sun is currently less than 5 billion years old, merely middle-aged. From this, it can be seen that its generation most likely belongs to the grandchild generation. For third-generation stars, their size is already quite small, but being small has its advantages, namely an extremely long lifespan, especially those little red dwarfs. Due to very slow fusion reactions, their lifespans can typically reach hundreds of billions, even trillions of years. This is truly living as long as the universe, in a sense. As the saying goes, the world is yours, and it is ours, but in the end, it belongs to these grandchildren, third generation. To sum up, searching for the previous generation remnants of the Sun currently faces two problems. First, it might not have any direct relatives at all. Second, after 5 billion long years, the universe today has long changed beyond recognition. Song Hai Song Tien. It's important to know that the solar system takes about 200 to 250 million years to orbit the center of the Milky Way once. That is to say, from the birth of the Sun until now, it has already completed at least 10 to 20 orbits. Not to mention that during this time, the Milky Way has also experienced events like merging with dwarf galaxies and all sorts of other miscellaneous events. Clearly, trying to find the Sun's relatives is an extremely difficult task. Although its birth parents are hard to find, we can try to look for the siblings born together with the Sun. Generally speaking, most stars are born in groups within molecular clouds. Our Sun is no exception. This story begins 4.6 billion years ago. At that time, in a certain corner of the Milky Way, a huge molecular cloud was dispersed. This molecular cloud might have come from residual material ejected by previous generation stars, or it might have contained primordial interstellar material. In any case, here, stars large and small were appearing one after another in clusters. Soon, an open cluster was born. Unlike globular clusters, which are like nursing homes for stars, open clusters are completely like kindergartens, except some stars grew up very fast. While their peers were still in the junior class, they had already reached old age. One day, our sun was playing happily with its little friends when a big star nearby suddenly self-destructed, went supernova. This explosion was no small matter. It not only blew askew the ecliptic plane of the solar system, but also caused the orbits of many small bodies within it to become bizarre. For example, the asteroid Sedna, with its extremely high orbital eccentricity, its perihelion and aphelion, now differ by over 800 astronomical units. Open clusters are inherently very loose. After being blasted by a supernova, it was done for, coupled with the gravitational pull from other surrounding molecular clouds. Soon the original cluster began to break apart. After only about 100 million years, with the disintegration of the cluster, a looser structure called a stellar association appeared. A stellar association is a group of young stars that have broken free from gravitational bonds, but are still moving in the same general direction. Because it originated from the previous open cluster, it's equivalent to these children having graduated from kindergarten and started school. But life in the ivory tower is also brief. Within a few 100 million years, these young stars would one by one step into the big society of the universe, starting to make their way alone. Because these stars come from the same molecular cloud, they share common characteristics and certain chemical elements. Additionally, in their early motion, they also shared a common direction. Considering their ages, they shouldn't differ too much either. Perhaps from these aspects, we can find clues to the sibling stars from back then. In 2014, a paper was published in the Astrophysical Journal. A research team claimed they might have found the Sun's first sibling star, HD 162826. This star is located in the constellation Hercules, currently about 110 light-years from us. It is a late-stage F-type dwarf star, currently slightly larger than the Sun, with a mass similar to the Sun's. Whether from chemical composition or dynamical analysis of its orbit, HD 162826 is currently the star most coeval with the Sun. For such a star sharing the same origin as the Sun, does it have similar planets around it? Unfortunately, near it, we have not observed any planets so far, and astronomers speculate that, whether it's hot Jupiters closer in or gas giants further out, they are unlikely to be present here. However, the existence of smaller terrestrial planets is not impossible. Facing a sun in its late stages of evolution, one wonders what civilizations on that planet, if any, might think. Although we have only found one sibling of the Sun so far, in reality, the Sun's siblings might be far more numerous than imagined. Earlier, people estimated that the number of stars born together with the Sun might be around 500, but subsequent research suggests this number might be an order of magnitude higher, approximately 2,000 to 20,000. However, among these, not many are similar in size to the Sun. Most are red dwarfs with masses of 0-point-something solar masses. For these low-mass M-type dwarf stars, we currently don't have many methods to conduct detailed chemical composition analysis on them. So, whether they are siblings of the Sun or not is difficult to identify. The good news is that the ESA's Gaia mission will play a key role in the Sun's family search, because one of its most important goals is to create a three-dimensional map of the Milky Way containing 1 billion stars. Since the Gaia telescope takes images roughly every 6 months, it can record the motion data of stars, thus inferring their past trajectories. In this way, it becomes easier to find those stars that intersected with our Sun at a specific time in the past. If we can then identify them further using chemical fingerprints, finding those long-lost siblings might be just around the corner. Alright, this is Lingma Talks Universe, making the universe easy to understand. See you in the next episode. Bye-bye.